Hi, this is section 1.4, and we're going to talk about continuity. Continuity will deal with limits. Please don't confuse limits and continuity. We'll do these first two warm-up problems in class. And then I want to get to the third one, where I don't have pictures yet, but we'll draw some pictures in here. And we want to look at the idea of continuity and continuous functions. With that, if we have a continuous function, it's really just what you think it is. If I have something that goes on forever, I don't lift up my pencil to draw it, it's going to be a continuous function. Now if I look at this one with a hole in the graph, that would not be continuous. So back here, this one's yes, continuous. This one is a no, not continuous. Now you cannot explain or defend that something's continuous or not by just saying, well, I lifted up my pencil. And we'll get to the definition here in just a minute. But that is kind of the idea. This would not be continuous. Even if I had a point right there, that would not be continuous. Then we also have another kind of jump. We might have this one. Something like that would also not be continuous because of a jump. All right, if you want to write some of those ideas down there, you may. Now, the formal definition is that f of c is defined. Well, a function is continuous at c if f of c is defined. So if I had some value c here, f of c is defined. And then the limit exists. And so as I go closer here, and I go closer here, I'm driving to the same place, so we do have the limit. Then the third condition is that both of those are equal to each other. So if I look at part B, the condition A is satisfied, and the condition B is satisfied because I do have a limit, but they are not equal to each other. So then this portion fails for this problem. And if we look at C, f of c is defined, yep. And does the limit exist? No, it does not. So as soon as we run into one of these that does not work, then our function is not continuous. So if we look at some examples, we have this one here, f of x is equal to 1 over x minus 1. I think you can see that at x equal to 1, we're going to have a vertical asymptote. And when we have a vertical asymptote, obviously it's not continuous. So it's not continuous at x equal to 1. Now you might say that on different intervals it's continuous. So from negative infinity to 1, it is continuous, not including 1. And from 1 to infinity, it is also continuous. For this one, we have a problem at x equal to negative 2, division by 0, so we are not continuous. But what we want to see is, we want to see if this is a hole or if it would be a vertical asymptote. And if you remember, we get a hole if we can factor and cancel. So this is x plus 3, x plus 2 over x plus 2. We can cancel, so we're left with x plus 3. So this function f behaves everywhere the same as it does as x plus 3, except for at x equal to negative 2. Now, the next problem, if we have the tangent from negative pi over 2 to pi over 2, the tangent's defined inside that interval, and it is continuous, and this is an open interval, so I don't have to worry about those endpoints. And so, yes, this is continuous. And for any value that I take in here, I would be able to satisfy all three conditions. First of all, that the value is defined, the limit is defined at that point, and then they're equal to each other. Then we have some more specific discontinuities. We have a removable discontinuity, which is a hole in the graph, and then when defined can make the function continuous. So sometimes we can fill in the hole. Non-removable discontinuity is a jump or an asymptote. You cannot resolve these two with just a single point. And so when I say a jump, it's a gap jump. It's not just a hole in the graph jump. What we can talk about, and we've mentioned this a little bit, but now we can get some notation for this, is one-sided limits. And so with one-sided limits, we can come from the right side, and how we write this is x approaches c, and then we put the plus sign after it. And this is of some function. And if we want to do left-sided limits, we can do the limit as x approaches c from the left of f of x. And so this is the right-sided limit, this is the left-sided limit. The negative is after the value. It gets a little confusing if your c value is, for instance, -2, x approaches -2, negative. Oh, well, just think of that as being the left-sided limit. Okay, so that helps you with the left. And this one is the right. So if the overall limit exists, remember that the limit from the right has to equal the limit from the left. So if I have a piecewise function here, let's talk about this. To be continuous, these things have to link up. In order to link up, the left-sided limit has to equal the right. If they're not the same value, then they will not link up. Well, let's check this. So if I take the limit as x approaches 2 from the left, that would be under this case where x is less than or equal to 2, and I have 0.5x plus 4. Well, I can do a direct substitution even though we have a point of interest there. I can still plug this in to find out where this function goes. And so this would be a value of 5. And if I do the limit from the right, that would fall under this situation, x squared plus 1. Direct substitution gives me 5 as well. Since this number is the same, these did link up, and thus we have a continuous function. So we would have continuous. The next example, is this one continuous? And what we want, you look at these type of problems, what you should do usually is just figure out if they have a hole in the graph. So I'm going to factor this one, 2x and x. I'm going to guess it's a -5. Let's see if the factor 1 there works. So it's 1, -10. Sure enough, it does work. And this is x minus 5. They cancel, so I have a hole at x equal to 5. And so this is not continuous, but it's a removable discontinuity. Now what they might ask is, could you define a point that makes it continuous? Well, sure we could. If I know the x value, then I can find the y value. If I plug it into my original, I'm going to get 0 over 0. But since I factored and canceled, I kind of resolved some of this, so I can take the 5 and plug it into this. Because this 2x plus 1 will behave exactly like this original g function everywhere except for at x equal to 5. All right? And so if I take 5 and plug it in into 2x plus 1, I'll get the point 511. Now I went back here, I called this g. I should probably not call it g. You can call it some other function. It's not exactly equal to g once I cancel. Composition of functions. This one, remember that this g is inside the f function. And so we have to look at, well, you can do it one of two ways. You can look at what you plug in and see if it satisfies the domain of the function that you're plugging into. Or you can just do a composition of functions and look at the overall domain. Since this is g of x, and that's going inside of f, that means that when I look at f, f does not equal 6. Well, if I plug g in there, that means the y-coordinate of g cannot equal 6. So if I look at this, x squared plus 5 cannot equal 6, and so x squared is equal to 1. So x cannot equal plus or minus 1. So for our domain for f of g, I cannot plug in 1 or -1. And if I actually do a composition, f of g of x, this would be 1 over x squared plus 5 minus 6, which equals 1 over x squared minus 1. All right? So with x squared minus 1, I need the pen. Okay. Then I get plus or minus 1 again. Now the last thing that we cover in this section, and you'll have to do some homework on, is the intermediate value theorem. This one comes up quite a bit, and under certain scenarios that, there's some good reasons to use it and just some other reasons. If f is continuous on a closed interval from a to b, and k is any number between f of a and f of b, then there is at least one number in C, or number C in AB, such that f of c is equal to k. Let me draw a picture. This is the easiest way to do it. That means that if I have a value here, and I have a value here, and somehow I have a continuous function, this is f of a, and this is f of b. Somewhere in the middle, if I say that I have a k value, well, what this theorem does, it's an existence theorem, so it guarantees me a value c that will match up with this k value, a y value of k. And that's pretty much it. Continuous function, to get from here to here, there's only, I got to pass through every point that's in between somehow, every y value, and in this case I pass by the k. Now where would this be useful? I think the most useful place for this is that if I have, for instance, a t-chart here, and I have some specific values. If I have some y values that are associated with these x values, if I look at this and I know that I have a continuous function, I know that between a -1 and a 2, that somewhere in there I have to have a 0. So there's some k value, no, k is the x value, but if I have this y value, excuse me, if I have a 0 in here, then I know that at x, there's some x value here that will give me a 0. So the 0 exists in there. And then here I have a 0 as well. So that's the most useful place for the intermediate value theorem. All right, thank you very much. You can try a couple of problems if you want, but otherwise we'll do it in class. Thank you.